Bismillahirrahmanirrahim. Assalamualaikum and a very good afternoon. So today we are going to step in the fifth chapter of the course, discussing on the basic filtering and also the bot plot.
Today we are about to steps in chapter 5 discussing on types of filters, transfer function and frequency response. We have discussed 3 types of filters in chapter 3 in Fourier transform applications. To begin with, let's have a quick recap on different types of filters and their specification. Generally, a filter is used to filter out or remove unwanted frequency components, while retain components in a given range of frequencies. There are 2 types of filters, which are the active and passive filters. We are going to discuss passive filters in this course. The frequency range over which the output is significantly attenuated is called stopband, while the frequency range over which there is little attenuation is called passband. On the other hand, the cutoff frequency, C, is defined as the boundary between passband and stopband. Bandpass filter and bandstop filter are dependent on 2 cutoff frequencies. Bandpass filter accepts frequency component or signals within its cutoff frequency limits, while bandstop filter removes signal in between its cutoff frequency limits. Next, we are about to look at the frequency response, which represents the filter behavior across frequency ranges. Let us look at the first example on a low-pass filter. In ideal case, the frequency response appears as a square signal with sharp edge separating the passband and the stopband. The passband gain or its amplitude is 1, while the stopband gain is 0. In addition, there is no transitional band in between passband and stopband. On the other hand, in practical case, the passband gain or its amplitude is not exactly 1, while the stopband gain is not equal to 0. There is no absolute band-stop value in practical filter. Meanwhile, transitional band exists in between passband and stopband. Page 7 to page 7 represents the filter response for high-pass filter, bandpass filter and bandstop filters. The green or blue area represents the ideal case passband frequency areas in ideal filters, while the green line represents the practical or non-ideal filters cases.
Okay, next is the transfer function. So we have seen transfer function earlier in chapter 3, Fourier transform. So basically the transfer function shows the relation between the output and the input of a system. So for example, in a filter, so the transfer function H omega is given as the ratio between the output amplitude and the input amplitude. So H J omega, so that we have seen in chapter 3. So it's basically the ratio between the output amplitude divided by the input amplitude. Okay, while the phase of the system is basically the difference between the output phase and the input phase. So theta, the phase difference between the output minus the input phase. Okay, in chapter 3, we have used the transfer function in omega domain. So in chapter 3, for a transform, we use the omega domain. But in this chapter, chapter 5, we are going to use the S domain to analyze a filter or the relation between the input and the output of a system. So the magnitude and the phase as shown from a transfer function basically shows how the system is affected by the complete network. Okay, let's look at the first example on a circuit. So basically a circuit represents a network, so in which shows the relation between the output and the input. So in this case, we assume that the V1 is the V in, the input, while V2 is the V out. Okay, so we know that in this case V in equal to V1 and V out equal to V2, in which V2 we can get it from a voltage divider equal to V1 multiply with 1 over SC divided by the total impedance R plus 1 over SC. So as I mentioned earlier, that in this chapter we are going to use S domain to analyze a system. So in this case, the first step, you need to convert the given circuit into S domain circuit. So assuming the given circuit there's no initial value, therefore you don't need to consider the additional voltage source. So in this case, the circuit can be represented in S domain as this. So this is your V2S, and here is V1S. R stay as it is, while C becomes as 1 over SC. Therefore, V out equal to V2, in this case equal to V1S multiplied with the C in S domain divided by the R, the total impedance R plus 1 over SC. So you can simplify the equation into this. So this is the ratio between the output and the input, basically shows the filter transfer function. So in this case, S is also equal to sigma plus J omega. So in steady state condition, the sigma or the conductivity equal to 0. So we can assume S equal to J omega. Therefore, we can analyze the network or the system performance at certain frequency by replacing the omega with the required frequency values. So the magnitude of the transfer function or the filter can be calculated by calculating the magnitude of the function, while the phase can be calculated by using inverse tangent of the component. Okay, let's look at the second example. Given a transfer function in S domain, so you need to evaluate the given transfer function at specific frequency omega 1000 and omega equal to 3000 radian per second. So we have seen in the earlier slides that S equal to J omega, assuming that there's no initial function and the system is basically in steady state condition. Therefore, you can replace all S with J omega. So same goes to this S and this one as well. So then you can replace all omega values with the first one, omega equal to 1000, and the second one at 3000. Okay, so at omega equal to 1000 radian per second, so in this case S equal to J omega. So we replace omega with 1000 in this case, then you will be having the complex equation in rectangular form. So finally you need to convert the equation into polar form. So you get the transfer function or the filter performance at 1000 radian per second. Okay, next you need to repeat the same steps for omega equal to 3000 radian per second. So the same equation, S being replaced by J omega. So now omega equal to 3000 radian per second, and we get the value at omega equal to 3000 radian per second. Okay, let's have another example on circuit analysis. So in this case, you have a series of R and L in the circuit. So as mentioned earlier, you need to convert the given circuit into S domain circuit. So this is R and L, and this is the source. So please take note which one is V in and which one is V out. So in this case, you have the V in S domain, and L become SL, and R stay as it is, while V not as on the left hand side. So as usual, to get the transfer function, H is the ratio between V out over V in. So we know from the given circuit, V out S using voltage divider equal to V in S multiply with R divided by the total impedance, so R plus SL. So in this case, and then V in equal to V in S in this case. So the ratio between the output and the input given by the H transfer function, so V out S divided by V in S. So this is your V out divided by V in. Okay, so V out divided by V in equal to R divided by R plus SL. So then you can evaluate the performance of the system at different frequency values by replacing the omega into the S component, so J omega. Then you can calculate the magnitude of the transfer function at specific frequency and also the phase difference. Okay, with that, I end the first part of the 5th chapter. Next, we are going to discuss on how to draw or sketch the frequency response of a filter by using specific equation or function. Thank you.